Okay, last we looked at our what? We looked at our PIPO power in result. There's our power in, okay, and obviously we explained our power out a long time ago. Now, you can therefore retire the PIPO, the power in result. We can retire that one there. What we're going to do is we are going to look at the final one, which is our what? Our para in, para out. Oh well, gonna cause me traffic issues here. I can see it already. Okay, let me move this one also a little bit. Let me move this a little to the side. This was the control. Okay, so I want to avoid too much traffic here. All right, so when you are controlling, maybe I can move you here. Yeah, when you are controlling our output, we saw how we can use an AND gate, but the AND gate, when the signal that needs to control is a 1, an AND gate would work perfectly because 0 blocks whatever you want to send through, 1 sends out a 1. So if you want to control with a 1, that is easy. But we've seen how with an AND gate we can control. If you want to control with a 0, if you want to control with a 1, we use the AND gate. If you want to control with a 0, we use a what? We use an AND gate. All right, now we've explained how we can what? How we can now we can do that with in our previous session where we had para in. So we know how para in is done from our last session. Now para out we also did in the other we did the para out. We said we just need to bring back that control of an AND gate. I will need to control that one to say when my data is nice and ready, I can have it out. Need to control that one too with an AND gate because my data must come out whatever it is. I must not change it. So 1 must be able to go out, 0 must be able to go out. That's easy with a what? With an AND gate. Okay, with our AND gates, we've done PIPO already, so we know that yes, we still get what I do there. Was it necessary? Nope. Yes, we can still access our series output, still have our series input. Parallel output can be fed in, and then we control with, in this case here, an AND gate, which we've done with PIPO. All we're doing is combining PIPO and PIPO. Okay, so this here is control. 1 blocks the AND gate, 0 blocks AND gates. So this is a 0 for hold. Let me rather call it a hold than a block. Hold while you're still busy, and then 1 we say what? Load, allow it to go through. Alright, that for me is better language than what? The better language than the other one. So now there we can take our parallel output. So in our previous scenario where we had 1 0 1 0, we know that this is our parallel output. Okay, so where we had 1 0 1 0 0 1 0 is our what? We loaded through the what? Through in parallel. Now we can say with 0 all the time we would have had the control at 0, so it would have our output wouldn't be able to come out. Then when you say load with a 1, 1 and 1 will give us our 1. 0 with anything will go immediately to 0. That will go to 0. 1 and 1 will give us our 1. So our output will therefore come out. Probably let's just name the outputs for what? For is. Doesn't matter what you name it, as long as, because this is A out, I'll call it out, out. Doesn't really matter. You can name it anything just to differentiate. This is our A in, our B in, our C in, and our D in. Okay, you could say Q whatever, doesn't really matter here. Okay, when it comes to direction, we already looked at how we do left or right or whatever. Okay, in this case we're not really fussing about direction, we're worrying about how we load in parallel. And so as you can see here, once I say load, my data goes out same time. When I say load the output, my load for the output comes out same time. So this is the fastest, actually what? This is the fastest shift register that we have. All right. Now, if you further wanted to then take our output in series, you remember that the clock pulses will then not allow us, in this case here, using the trailing edge. Okay, because the what? It's a master slave type. All right. So this is probably the shortest video I've done so far on the what? On the shift registers, because I think most of the work had been done in the previous instances. So thank you. I hope you understood. I hope if there's questions, I can get what I can get. I'm seeing the negligence. Our clock is not indicated there. Probably in our last session also, we may have forgotten to what to name our clock. All right, go back to the previous session and just name that clock there. So you can see again. Note that it's what the clock is actually synchronous for all the what? For all the clock pulse, for all the flip-flops, and then so that they open at the same time and allow data to flow. All right. And also remember that the size of delay, the number of flip-flops determine the number of clock pulses delay. So if we have three, we have 3 clock pulses delay. If we have 1, we have 1 clock pulse delay. The delay is what? Is actually delayed by 1 clock pulse. All right. Again, depending on whether we're using what? We're using leading edge. Is true for all trailing edge ones, but for the leading edge ones, the entry one is always what? A half. The delay there would be what? Would be half the clock pulse. All right. That being said, I believe on shift registers, if there's one last thing that I might probably still emphasize on, it will be the what? It will be the timing diagrams. Okay, the timing diagram on the what? On the shifting, maybe shift left and shift right. All right. With that, I will see you another time for another session.